Hello, everyone. I'm Ali Madani. Just a little bit of update. Went through an acquisition. I'm now senior data scientist in the company that bought us in Recursion Pharmaceutical. So here's my LinkedIn profile and my Twitter if you want to keep in touch. But today I'm going to talk about explainability in boosting machines. I'm going to keep it short. You're past 7:30 already. So I don't want to get into details because half an hour is not enough, definitely, to get into details of boosting machines and how to use explainability. But I'll leave you with a point to learn further about these subjects. So the first thing that matters is to know what components matter when you want to build machine learning models. So these are 8 of them. So you need to care about generalizability and high performance, right? But it's not only about training and testing and using accuracy. So you need to know what statistical measure to use, how to come up with proper and reliable testing strategy. And it's not as simple as just using different cross-validation techniques. Sometimes you need to come up with something that fits into your problem. I can provide you an example at the end of the talk. You need to make sure that you have some sense of explainability in your model because that provides you evidence and that provides you tools to improve your models and come up with more reliable models in production. At the end of the day, we care about production, right? We go through the whole machine learning life cycle, select data, do data wrangling, featureization, representation learning, training, testing, but at the end of the day, it's all about production, right? So we have to make sure we take care of these components to come up with reliable model in production. Another one is fairness. Fairness might not matter in all subjects and all domains, but if you are working with clients, if you are working with patients, if you in any way work with human being, fairness matters. But bias is not just about fairness. In general, it's a general term that you need to care about when you build your models to make sure it's not biased to a specific data point, feature that could be problematic at the end of the day for you. Model monitoring and maintenance is another important feature. So these are all different subjects. Some of them are under ML ops, some of them are all under ML research. So you might hear different job titles, different kind of areas and books in each one of them. But these are different components that matter when you develop your models. And causality is another one, test-driven development. Today, we want to focus on 2 of them. One, we want to make sure we have a generalizable model. I'm not going to get into too much of how to design your testing strategy, but I want to touch on explainability and try to make sure you understand what's the balance between having interpretable model and high performance model and how you can use explainability to not just have high performance model, but provide some information regarding how exactly your model is using the features to come up with its decisions. So we're going to start with decision trees. Very simple. So right now, maybe most people don't even use it, although maybe till 5 years ago, most banks were already using it. Why? Because they're interpretable, right? We know how exactly decision trees come up with their decisions. But to make sure we're all on the same page, because I don't know about your background, just a little bit of review of how exactly decision tree works, and then make sure you understand why we consider it interpretable, right? So decision tree, very simple. If you have one level decision, you can have a feature I in this case, and say, okay, if it's continuous, we split it based on a specific threshold. If it's binary, if it's categorical, we can use those information to come up with a decision saying that, okay, these data points should be considered as one class in the case of classification, and then these data points should be considered as another class, right? So, and then based on overrepresentation of one class versus another, we say that, okay, this node is now class 1, whatever comes to this node is class 1, whatever goes to that node is class 2. Very simple. So if you have, I'm not going to get into math, but if you like math, this is how exactly that decision is made. So you can have entropy, you can have Gini index. Based on all those measures, you can come up with proper decision. and then calculate how exactly decision tree should choose the feature that can discriminate the data in best way possible. Because usually you have 1,000 features. Which feature you want to choose? So you have a statistical ways of doing that, but it's all the time behind the scene. You don't do it. So when you develop a decision tree, random forest, light GBM, XGBoost is all behind the scene, right? This is an example I mentioned. If you have, for example, binary data, very simple. So if you have a data point in this node, interpretable. You know why the model is saying it is class 1 versus class 2, but you can have categorical features which are not necessarily binary, or you can have continuous features which is used here to categorize data based on specific thresholds. Very simple. Maybe 95% of you already know it. I don't know the background. Sorry if it bores you, but just to make sure we're on the same page. But imagine we have even a deeper decision tree. It is still interpretable because you can go back in the tree to find out how the decision is made for a specific data point, right? How different features going from I to K to Z to S have been used to come up with the decision of saying that, okay, this data point now is class blue or class 1 or 2, just depending on how exactly you're coloring it, right? It is interpretable, right? But there's a problem. It's not generalizable. So we know decision trees are not good models, usually, most of the time. They are not generalizable. They are prone to overfitting, okay? So we have this interpretability on one hand, and we have the problem of generalizability and high performance on the other hand, right? So now the question is how we can benefit from decision trees and then try to come up with high performance models. And the answer that has been there for many, many years, more, even before the current hype in deep learning, is ensemble modeling, right? You've heard of random forest, boosting, XGBoost, light GBM, and all these kind of methodologies. But all of them goes back to this theorem, Jury theorem, right? The idea is simple. If you have 5, 10, 20, if you have multiple people that decide better than random, if you have multiple models that decide better than randoms, if you have multiple tools that decide better than random, if you combine the decisions, the decision usually works better than each one of them across different data points. And it makes sense, right? So this is the idea behind ensemble models. Random forest is an ensemble model. It's a bagging model. It's a bootstrap aggregating model. Today, we are going to talk about boosting, which is another category of ensemble models. And I'm going to get into a little bit more details. So I don't want to go to the end for question. If you have any question, interrupt me. That's totally fine. So this is the idea of boosting. So when we want to build the ensemble of trees, the idea is I have decision tree 1, decision tree 2, decision tree 3, 4, 5, till 100, 200. If you use scikit-learn for all ensemble models, there is a parameter n estimator. That's the number of decision trees, right? That's going to be built, right? The question is how exactly the algorithm behind, the code behind it that works based on a specific algorithm, build those decision trees. In boosting, the idea is decision tree 1 makes predictions, but some of the predictions are wrong. But instead of letting the next tree to be built based on random features and random data points and not paying attention to the previous decision tree, we want to go sequentially, right? Decision tree 2 cares about the mistakes of decision tree 1, right? So there will be some sort of overweighting of the data points that have been mistakenly predicted as class positive or negative if it's binary classification. And decision trees will be built sequentially in this way as we go. So at the end of the day, we will have 100 decision trees or estimators or 200 decision trees or estimators, or how many you want, right? Usually more than 500 doesn't matter. So, and then at the end of the day, each one of these models or decision trees is a predictor for you. And then you can combine these in a weighted manner to come up with the predictions. Nowadays, you won't do it. So it's all behind the scene in scikit-learn. But what matters is how you approach using different algorithms. Why exactly people say XGBoost or LightGBM works for tabular data, right? Why the go-to algorithm when you're working with tabular data is usually boosting machines, right? Especially if you have a low number of data points. And by low, I mean compared to millions that we usually use in deep learning. But let's go through another visualization to understand it a little bit better. So we have this process. There's a concept for level-wise tree growth and leaf-wise tree growth. I'm not going to get into all those details. But the idea is we want to let the trees to grow, right? Because that's the way that we can let the trees to become better and better and predicting for the data points that have been mistakenly predicted as one class versus another, right? So, but if we pay attention to each one of those trees here, this is an example. It's from a paper. I chose this specific example because the visualization looks okay. So here you see the decision making is interpretable. For example, if it comes here, we know that it's elder, it's adult, and it's male. It's not male, right? And it comes to this node. But when we build this ensemble of decision trees in XGBoost or LightGBM, the model will not be interpretable because each decision is a combination of all those trees. Features are contributing through different decision trees to come up with the final prediction, right? But before getting into explainability, just one notion. So maybe 10 years ago, most of the books, most of the courses have been in Python machine learning, Python machine learning training, right? So machine learning training is simple, is very simple. Coming up with reliable machine learning model is hard, right? And reliability is about all those components, right? Generalizability, fairness, proper testing, monitoring and maintenance, and all those factors that I mentioned there, right? And this is an example of that. So we are loading the data. As adult income data is very famous. If you have been working with SHAP, which is an explainability library, I'm going to get into a little bit later. So we add this data, we load the data, we split it, we initialize the model, we fit or train the model, and then we come up with the prediction. And this is the case for almost every single algorithm that you use in Python, except for deep learning from PyTorch and TensorFlow, which is a bit more complicated, right? So this part is simple. Now the question will be, OK, how exactly should I split the data? This is a horrible way, right? Usually. So now the model is built, right? How exactly should I know if the model is using the right feature? There have been many studies. So I remember from a PhD, there was a study in genetic, right? And all the findings was based on the time that the measurement happened. It was nothing to do with genetics. So different labs did different measurement through time. Today, next day, the day after. And then they figured out that the whole discovery that got published, I don't remember, it was Science, Nature, or something. It was all based on the time that the measurement happened. It didn't have anything to do with those features that they thought are contributing in the predictions. So boosting machines, now not interpretable, but generalizable, right? We had decision trees, interpretable, not generalizable. Now we have boosting machines, generalizable, not interpretable, okay, by default. So what we can do, which is not only for boosting machines, you can do it for bagging models like random forest. There are different techniques for deep learning. For example, in convolutional neural network, you have saliency maps or different kind of techniques that apply for each one of them. But you can use explainability. That's the whole idea of explainability. You can use explainability to not lose performance, to not lose generalizability, but try to come up with reliable model. Okay. And this is how it works. Again, Python code, very simple. So the difficulty, you see those big repos, it's just a matter of how to come up with clean code, test-driven development, to have all the unit testing, sometimes integration testing, different kind of thing. But if you have a Jupyter notebook, you can go through it from, I don't know, line 0 to 20, train, test, come up with explainability, and that's it. But that's not ready for production, right? So here, 3 lines, and we can easily come up with some explanation for our model. So first of all, we are choosing a tree explainer. So SHAP is a library in Python. Pip install SHAP, works beautiful. So tree explainer works for tree-based models, all tree-based models, like GBM, XGBoost, Random Forest, all of them. Because they are based on decision trees. And then you are calculating SHAP values. I'll explain how SHAP works. I will not leave you blind in that part. And then you can have different plots to tell you how exactly features are contributing. Okay, but a little bit on how SHAP works. So the idea behind SHAP is, so maybe you've done some feature perturbation, just change values of features and then see how they're contributing, right? How SHAP works is, instead of trying to do one by one, it considers contribution of each feature in different combinations. It's like 1 or 2 of them together or 3 of them together, but it doesn't do all the combination because it could go exponentially to a large billions and trillions, right? So it does some sort of random sampling for different combinations and use those samples to come up with the explanation. So that's how SHAP works. And it usually works well. But for explainability, you have different techniques. SHAP is not the only one. So, and just one thing I didn't explain here, but if you go to the literature, you want to read more, there are 2 notions in explainability. One is global explainability, and the other one is local explainability. Okay, just 2 terms there. If you want to get deeper into it, if you're interested, we can talk after. So, simple, right? We have these features. So these are the features in the data set. Usually the modeling that you do, at least I do, I'm dealing with more than 500,000 features most of the time, even if I do tabular modeling, tabular data modeling, right? This case is very simple, right? We have, I don't remember the exact number, how many, I don't want to count it, but around 10 features, right? So what we see here is, first of all, I don't want you to care about this is, for example, occupation, this is work class race or something. You need to learn how to use, how to benefit from SHAP, right? So if you have values to the right, so bigger values, it means that those features are having more impact in the predictions, right? One example is, imagine you have the first one with big magnitude and the rest of them very low. Any idea what that means? What could be the problem there? So we want to practice how exactly we can benefit from explainability. So imagine you have a model, the top one, you have high magnitude, meaning high impact, high contribution, but the rest of them are close to 0, 0.1, 0.2. You want to brainstorm? Any idea? Any suggestion? Pardon? Sorry, I cannot hear you. So it has high correlation. So from modeling perspective, you are in the right direction. What could it mean? So you have a feature with very high correlation driving the entire prediction. So you have 2 choices there. Either your model Either you have features that don't matter or your model cannot benefit from the rest of the features, right? Or you might even have data leakage. You might have a feature that is actually highly correlated or maybe even a representative or a surrogate of the output among your features. So instead of coming up with a multivariate model, what we have here is more of a univariate model. We have 1,000 features, but one or two of them may matter more. So these are different things that you can do when you use explainability. The other thing, I'll go back to. So the other thing is, so you can also use explainability for fairness to see what features are driving the prediction. Is it race? Is it sex? Is it different kind of proxies for sex and race that we care about when we want to do fair modeling, right? Question. So that's feature importance. Yeah, exactly. So what I mentioned is, so SHAP, instead of doing it individually, perturb your features, SHAP does it for you, but it consider contribution of feature in different combinations, like feature 1 and 2, feature 1, 2, 3, feature 1, 2, 4, feature 1, 2, 6, feature 1, 2, 3, 4, 5, right? So these combinations also take into account. So if you, I don't want to get into jargon, but it calculates marginal probability for each one of these combinations and then come up with explainability instead of just perturbing each one of the features. Exactly. So SHAP does bootstrapping. Yeah. SHAP samples. Yeah, that's exactly the problem. SHAP samples, but usually the sampling works well. Pardon? Okay. Yeah. So that's the thing. So in general, the model is coming up with nonlinear relationship to come up with the prediction, right? But the explainability techniques like SHAP, LIME, counterfactuals, all those try to provide you some insight regarding how the model works, right? So definitely it doesn't tell you about the nonlinearity of the relationship. Definitely, as you said, it doesn't consider all combinations. So it's somewhere in the middle. So the theoretical aspect of SHAP is all combinations. The implementation is bootstrapping. So it tries to bootstrap sample different combinations to come up with some sort of surrogate for the ideal case. So yeah. For the explainability, yeah. Yes, and I'm going to go back to that. So regarding different kind of things, yes. There are techniques. So because you want to make sure that you're not losing the insight for a specific part of your feature space, right? To just do all the sampling for a couple of features, and then some of the features will be left alone, right? So there are techniques to handle that to make sure you have good representation of different features in the feature space. Yes, yes. If you want, just message me. I can send you some resources for that. Was another question? Yes. So for multi-class, so for multi-class, so you have different choices. So one is to consider to focus on one of the classes. It's just one versus all kind of explainability, which is usual. So this is how I've been doing it, because usually you want to focus on one class and then see how exactly features are contributing. But I don't know if it can reports for multiple kind of classes all at once. I've not done it. Yeah. So going back to this, because I think we're short in time. What time is it? Yeah, it's 7:55. So going back to these notions, we had all these kind of subjects. The problem is, so when you learn about machine learning coming from academia or from different fields, usually we go deep in one subject, either from it could be MLOps or a specific application of machine learning, and we lose insight regarding all these kind of components that matter. You don't need to become expert in these, but you need to know them to be able to benefit from them whenever it's needed. So for that reason, I've been working with Pact. So I wrote a book. It's almost at the end. So, and we are going to publish it very soon. I think it's going to come out in fall, but we're going to announce it very soon. So the idea is to provide you with the techniques, Python implementation for all these subjects: explainability, fairness, test-driven development, which matters a lot. So causality, all these kind of subjects as a starting point, not getting too deep from mathematical perspective or implementation perspective, to provide you all these kind of tools to be able to benefit from them whenever you need them. So I think we went through a ton of questions, but if you have any further question, I would be happy to answer. Just I have one more point. So in explainability, so sometimes you want to have information regarding how features are contributing, right? Like in feature perturbation or feature importance or SHAP. Sometimes you want to come up with information regarding data points locally, how the decisions are made locally for individual data points, or how you can come up with counterfactual data points or alternative data points with a specific class, right? And there are techniques for that. So LIME is one of them. Unfortunately, half an hour was not enough. So LIME is a technique that provides you information in the data point side. So to tell you how exactly features are contributing in prediction of a specific data point or part of the feature space. Or you have counterfactual explainability that provide you examples that help you, for example, in banks. You want to suggest to somebody, do this, and in a year, you might become eligible for a specific loan, right? So those alternative examples are something that counterfactual example can come up with. And then you need to interpret how exactly those suggestions are meaningful, right? You cannot suggest somebody, okay, in a year, become 80-year-old, now you're 30, and then you become eligible, right? So these are all the issues with these kind of analysis. So you need to know how exactly to benefit from these techniques in your specific project. Yes. So linear is linear is definitely there. So we have SVM, I think, is applicable. I've usually used it with tree-based because it's just tabular data. So the data I've been working with is just large data. I think I remember I used it for SVM. So what else do you have in mind? I've not used it for deep learning, no. No, I've not used it for deep learning directly. Pardon? Oh, yeah, sorry. But so just, okay, just one thing if you can continue. So depending on data modality you have, so if, for example, you have images or you have text, there are specific techniques for those. Like, for example, in CNN, you have saliency maps that tells you how exactly the pixels are contributing the predictions. And so there are some ways of using SHAP for fully connected neural network and multi-layer perceptron. But usually that's not the go-to algorithm.